Today, we are cracking the code on one of the most powerful and, honestly, one of the coolest concepts in all of mathematics, exponential functions. And look, these aren't just some abstract equations you find in a textbook. Nope, they are the hidden script behind things that grow incredibly fast or, well, just fade away. Okay, let's jump right in.
It sounds like the start of a really weird joke, doesn't it? But the answer is that they're both running on the exact same mathematical engine. It's kind of mind-blowing. One explodes into our lives, and the other slowly vanishes from the world, and exponential functions describe both of those journeys perfectly.
So what is it that makes these functions so special? What's the secret sauce? Well, it all comes down to one tiny but absolutely game-changing detail: where the variable is. I'm telling you, it's a simple move, but it changes everything.
Okay, so here's the official definition. In an exponential function, our variable, good old x, isn't down on the ground level as the base. No, it's up in the exponent. That little x floating up there, that's the entire engine of all this crazy, rapid change. Now, this is where it gets really, really interesting. Most of us are familiar with a function like y equals x squared, right? The x is the base. That gives you that nice, predictable, symmetrical U shape. But shift that x up into the exponent, like in y equals 2 to the power of x, and the whole game just changes. You get this dramatic, steep J-curve that just rockets toward the sky. It's a totally different beast.
All right, so let's dig into how this one type of function can have two completely different personalities. I mean, it can tell a story of explosive growth or one of steady and inevitable decay.
And wow, this image just says it all, doesn't it? It perfectly shows those two sides of the coin. On the left, you've got those classic J-curves just shooting upwards. That is pure growth. And then on the right, you see the mirror image. Curves that start high and then just fade away, getting closer and closer to zero but never quite touching it. That, my friends, is decay.
So how does the function know whether it's supposed to grow or decay? Well, the logic is actually surprisingly simple. This quote from our source material lays it out perfectly. It all comes down to the value of that base number. So here's the crucial point, the main takeaway. It is all about the letter b, the base. You can think of it like this. The entire destiny of the function, whether it's going to soar to infinity or sink towards zero, is decided by this one single value. And here's the rule, plain and simple. If b is any number bigger than 1, we call it a growth factor, and our function climbs. If b is a number between 0 and 1, like a fraction or a decimal, we call it a decay factor, and the function falls. It really is that straightforward.
All right, we've got the core rule down. Now let's learn how to actually spot these factors in a real equation. It's time to put on our equation detective hats.
This right here, this is the standard blueprint for pretty much every exponential function you're ever going to see. Y equals a times b to the power of x. Now, a is just your starting amount, your initial value. But b is our hero. That is the growth or decay factor we've been hunting for.
Let's walk through this one together. We see the equation. Okay, step 1, identify the form. Yep, it's a perfect match for y equals a times b to the x. Perfect. Step 2, let's find our b value. In this case, it's right there. It's 3. And now, for the final, most important step, we ask the key question. Is 3 greater than 1? Yes, it is. And boom, just like that, we know this equation describes exponential growth. It's as simple as that. Okay, now this is where it gets really, really cool, because this math isn't just locked away in textbooks, it is all around us, shaping everything from the money in our wallets to the very atoms that make up the universe.
Let's start with a growth example that affects every single one of us, the cost of living. So our source material uses the example of a 4% annual increase. Now, you might think, 4% isn't that much in 1 year, but because it's exponential, that growth compounds. That means it builds on itself faster and faster over time. And this slide shows you exactly how we translate that percentage into our b value. You take the percent, turn it into a decimal, so 4% becomes 0.04, and then you add it to 1. Now, why the 1? Well, you want to keep 100% of the original cost, plus that extra 4%. That's why our growth factor, our b, is 1.04. All right, let's switch gears and look at the other side of the exponential world. And there's no better example of decay than radioactivity. The core concept here is something called half-life. It's the fixed amount of time it takes for exactly half of a radioactive substance to decay. And as the source points out, it is a perfect real-world case of exponential decay in action.
Just take a look at this table for thorium-234. Every 24.1 days, like clockwork, the amount remaining gets cut in half. It's being multiplied by a decay factor of 0.5 over and over and over again. And notice our B value here is 0.5. And what do we know about 0.5? It's between 0 and 1, fitting our rule for decay perfectly.
Okay, we have covered a lot of ground here, from the shapes of the graphs to real-world stuff, so let's lock it all in and just summarize the most important rules of the game to take away from all this.
Here it is, your essential cheat sheet. Remember, the magic is all in the exponents. That's where you'll find x. The base, b, that's the storyteller. If it's bigger than 1, it's a story of growth. If it's between 0 and 1, it's a story of decay. And a, well, a is just where the whole story begins.
So there you have it, the secret code behind some of the most dramatic changes that shape our entire world. The next time you hear about compound interest, or population growth, or even a viral social media trend, you'll know the exponential engine that's driving it. The only question left is, where are you going to spot it first?